Very afternoon, ladies and gentlemen. Last session for today, and we kept a little bit, the cherry of the cake for the evening. So you have to use your brains, I'm afraid. Okay, you're free to ask questions, and even anything out of track, Harpreet will be able to handle that. Now, I'm very happy you came over. It was a very long way from Texas, the wild land on the other side of the ocean, and he's working with Jeff Andrews, my brother in crime. We have a very good relationship with him, actually, and you are apparently his star offspring. So I'm happy to have you here, and you have a very strong background in theoretical analysis, stochastic geometry, and we hope to hear some interesting analytical results, particularly in the light of heterogeneous cellular network deployment. The floor is all yours. Thank you.
Thanks, Misha, for a Thanks, Misha, for a really kind introduction, and thanks to you and Jeff for sending me here. It's a really great opportunity for a student like me to present my work in front of such a esteemed audience. So this work is going to be on, as you can guess, heterogeneous cellular networks, and this is actually in continuation with Guillaume's talk, in which he basically presented some numerical tools to understand how the addition of femtocells is changing how the cellular networks look like. But in this talk, we are going to take a more theoretical look and more fundamental look at how the networks are changing, and what are the theoretical tools that are available to maybe get some performance guarantees, how those networks are actually behaving. So this is joint work with my professor Jeff Andrews, and we have collaborators. First is my mentor Radhakrishna Ganti. He used to be a postdoc at UT Austin, and now he's the assistant professor at IIT Madras. And then we have a colleague, Tom Noblin, who did some uplink work with me. And then we have Professor Francois Bacelli, who is basically behind most of the theoretical stuff we do, and he is of really a great help in understanding stochastic geometry and using it in cellular networks. So the outline of this talk is, first I'll be giving a very brief introduction of why we need small cells. We have already had enough since yesterday. We have talks by Thierry, Joseph, Prabhakar, who have been giving a really good insights on why we need small cells, and giving a really good overview of how the networks are becoming right now. And then we will be developing a baseline downlink model, how you model downlink in a HetNet scenario, and how you develop tools to get some analytical results. And then there would be some technical challenges there, and we will introduce some notions of loads, of how the load on a femtocell can be modeled analytically, and that we will be doing by incorporating base station activity factor. And then yesterday we had a brief discussion about the differences between downlink and uplink. So I've included a few slides on the uplink model. How is it more challenging to study in the light of stochastic geometry and the HetNets? So we will have some basic results on uplink, and then the last part would be on spatial statistics. As most of if you guys know stochastic geometry, most of us we use Poisson models, but are they really applicable in HetNets? So we will be taking we have certain data sets and studying them and seeing whether Poisson are really applicable or not. So just a really brief introduction, actually a historical perspective. So until a couple of years, the design philosophy, as you guys know, has been to handle voice applications. That has been why the cellular networks were designed and deployed. So main goal was to provide coverage to all the users. So if suppose I am a cellular operator, I would like to reach as many users as possible. So that was the driving force behind deploying and designing these networks. And this led to an interesting, homogeneous deployment. First of all, we had single type of infrastructure elements, which were tau-mounted base stations or access points, whatever you call them. So they were really, homogeneous in that sense. And then secondly, we had locally homogeneous spatial deployments because we had to achieve coverage goals. You won't put base stations right next to each other. So if you see spatially, they were locally homogeneous in that sense. And why I use this locally homogeneous word here, it's because if you see an urban scenario and a suburban scenario, you'll always see the density of base stations being higher in the urban scenario. So that's why it's not going to be homogeneous over the whole space, but locally that is homogeneous. And then the deployments were also based on population density, as I said. So this led to, the networks were not really challenging. You could come up with a simple model and analyze them. That's what we have been doing so far. But recently, there has been some changes in the trends, the way we use networks. So there has been, urge to be connected to the network 24/7. You people, probably you use your Facebook right after, in the coffee break. So that's what have been happening for a few years now. You really want to be connected. Maybe it's your phone, maybe it's your laptop, maybe it's your tablet, but you want to be connected to the network. Even if you don't have anything to do, anything useful to do, you will watch a YouTube video. So that has been putting a lot of pressure on the networks. And focus, as I said, has been shifted towards data-hungry applications. But you want video streaming, you want real-time video chats, and that has been enabled by advances in hardware. You have advanced smartphones now. Until maybe 2-3 years back, you had those small, at least I had that small handset. You could only do 3 things. You could do a voice call. That's what you would do once a while in a day. And you could, send SMS, right? And the third thing you could do was basically play that snake game, that there was a snake and there were obstacles. But now you see your phones. You have perhaps everything you could think of. You can access internet. There is high-speed internet available. You can watch YouTube videos. So there has been, a really, if you haven't thought so far, it's just 2-3 years in which this whole change has happened, right? So now we have tablets. Very recently, I won't name, but they have been really, really successful, a big success. And then you have laptops. We had all those, data yesterday. I won't repeat. It was, I think, in theory slides. It was like, I think, hundreds of times more data usage because of these. And the message here is that the macrocells were clearly not designed to handle this kind of behavior. So you would expect some really fundamental changes in the network. So that's the only message here. And that's what we have seen. We have, increasing heterogeneity. We have different types of, infrastructure elements coming up. As you previously had high-power, tower-mounted base stations that we call macrocells. And now there is addition of, operator-managed pico cells being put at the hotspots and at the cell edges. And then you have user-installed femtocells, in which you guys are all interested in. And we also have small form factor distributed antennas, some dumb, antenna heads. So what this is doing, this bringing in, a lot of challenges which weren't there when you had macrocells. Now you have a challenge to develop a model which captures this heterogeneity, and at the same time, it is simple enough so that you can do some, useful analysis. Because simulations will take you, to some extent, it will give you some insights. But you really need some analytical background on this, and so that you can give some theoretical guarantees. So that's what the main challenge is, and that's what we will be, addressing in this whole talk. So since this is going to be centered around the cellular models, let's take a look of, what kind of cellular models we have right now. And this is, you guys would have seen it hundreds of times. This is a standard textbook figure. You have these cellular base stations. You have these macro base stations, which are located at the, which form a grid. They are located at the centers of the hexagons. The hexagons, they kind of depict the coverage. And this is what we call a standard grid-based model. And it has been reasonably successful in giving insights into, macrocells, especially by simulations. But if you think deeply, it is not scalable to multiple tiers. What would you do would you make another grid for femtocells? Would you make, another grid for picocells? So it is not clearly scalable in its, current form. And the second model is Wiener model. If anybody of you has been interested in information theory, it has been widely applied there. So the model is that you have a mobile and you have a base station. It connects to the, say a nearest base station. It doesn't really matter here, but the gain is considered to be 1. Now for cellular engineers, this is probably, the worst assumption to take. And then you have the interfering base stations, which is, the gain from the interfering base stations is considered to be a constant. So what this gives is that it does not have a notion of outage, since SINR is fixed and deterministic. It has been really successful in giving information theoretic insights, but in cellular this is not applicable. And then we have a third model. These studies have been around in mathematical fields for a long time, but for cellular this is really new. What we call random spatial model. In this model, what you do is that you assume that the base station locations are some realization of a point process. You might not know what the point process, underlying point process is, but you assume that these locations are maybe it's a Poisson process or any other process. So you assume them to be a realization. And you can easily see that because of this randomness, it is easily scalable. You could have as many types of base stations as you want in this kind of a model. So this is, and we will see that why these kind of models are more applicable to cellular networks of today, and why not this grid model. This is again a grid model, and this is an actual 4G deployment in the United States, a big city in the United States. And what these lines basically mean, if you guys know stochastic geometry, this is just a basic Voronoi tessellation. You have 2 points, you draw a bisector, and that's what you do for all the points, and you get these weird looking cells. And these are basically, I depict them as coverage. They are not really, because you have fading and stuff, but on an average, these are the coverage cells. And then you have this Poisson point process. So if you guys have had background in stochastics or stochastic geometry, this represents complete spatial randomness. So what it means is that conditioned on the fact that you have, say, n number of points on this plane, you throw these points randomly on a plane. They are kind of uniformly distributed given the number of points. That's what a Poisson process is. So, and we will see that, okay, one might say that for macrocells, this is maybe not a very intelligent model, but then so is not a grid model, right? So the reality is kind of in between of grid model and Poisson model. So I'm not saying that the Poisson is end of the world, but it is a good starting point. That's what this picture shows. And now the picture becomes really interesting if you add more types of base stations. Say you add femto and pico here. So I'm just assuming femtos and picos to be PPP, Poisson point process for both the pictures. This is showing an actual macrocell deployment, and this is all the tiers are, say, Poisson. So when I say PPP, that basically means a Poisson point process. So we'll be using this word a lot. So just kind of remember it. And in these two plots, we see that they are actually quite similar. Just eyeball tracking would say that they are quite similar.
Just a quick question. When we say that this PPP process is closer to 4G, the reason this process means this stochastic geometry is there for almost 2 decades, but the reason this model was not initially used is that it is unable to model the repulsion between the real base stations. Whenever a real operator goes to deploy a base station, it will always be inclined to separate the base stations. But this, as you can see in the left and rightmost figure, means there is the base stations tend to be, there's no mechanism to control the distance between the base station, and we will end up with having very close base station. This is one. And second thing, with the deployment of femtocells, do you change the density of this average density of Poisson point for femtocells?
Yes. So for your first question, as I said, this is just a starting point. We have processes in which you can model repulsion. I'll be coming at during my talk at the end. And regarding your second question, yes, we do change the density, and that's I'm going to explain in detail how you do that.
Okay, thank you.
Sure. So from these two plots, we see that they are quite similar. The actual scenario and the model, they are quite similar. So at least we have a good starting point in which we can use in analysis. So with this, we will develop a downlink model using this insights which we got, and we will model downlink here, and we will try to find some analytical guarantees on coverage. So this is what we propose, a proposed baseline random spatial model. We consider, to be really general, we consider k types of base stations, right? So you have k different types of base stations here. Like in this case, we have 2 different types of base stations, such as say macro or femto. In this case, you have 3 types of base stations, say macro, femto, or pico. So this model is a general one. We have k types. Then each tier has base stations which are taken from independent Poisson point processes. So we assume that the point processes which correspond to these base station locations are independent for each other for different classes. And then base stations across tiers, coming to your question, they differ in terms of 3 things. First, they differ in terms of the base station density. Of course, you'll have the macrocells to be really sparse as compared to femtocells. And then they differ in terms of transmit power. Of course, the macrocells would have high transmit power. And then we have this, it should be SINR target, which we call as betas of J. So I think SINR target was touched a little bit by Guillaume. So I'll just repeat what he said. So it is the minimum SINR required to establish a link with the base station. So we will use this fact, and this is going to be really important for our analysis. So we assume that the SINR target is different for all the tiers. Just note down these 3 parameters. These are going to be important. So density is always going to be represented by lambda, transmit power by P, and target by betas. And then we have this max SINR connectivity model. This is to associate users with the base stations. So we assume a typical mobile user connects to the strongest base station, which of course is not going to be necessarily the closest one because of fading. So we have max SINR connectivity here. And as for fading, we assume Rayleigh fading. We have already had a long discussion on propagation, so I won't explain what it is. And then we have this k-tier downlink model. And again, it is in continuation with Guillaume's talk. So you would have seen this equation there. So our first assumption, or basically without loss of generality, we could assume that the typical mobile user is at the origin. You have all these base stations, and assume that the mobile at which you will be doing your analysis is at origin. That is the first thing to note. And then the receive power is going to be the product of the transmit power into the fading component and a standard path loss, where alpha is your path loss path loss coefficient. So this is what the receive power is, and then the interference power is going to be the sum of the power received from all the interferers, which is basically the complete network except the base station to which you are camped to. That is going to be what the interference power is. And then you define signal to interference ratio as the received power from the camped base station divided by the net interference from the whole network. So, and we will, sure.
For the received power, you assume that the path loss is not yet integrated in the channel gain.
Yes.
Here.
Yes.
Is there a special reason why?
Yes, as you'll see, it is not really benign for analysis. Yes. That is really the honest reason to do that. You could so we have incorporated that and done some numerical studies, but the trends do not really change.
Okay, thanks.
Sure.
I think with the path loss, we are not able to assume the Wernoit tessellation anymore.
Wernoit tessellation?
Because Wernoit tessellation will be there if it's only distance based. Association is distance based, but the path loss is non-linear, so.
So it depends. Now, if you have all the base stations which are transmitting at the same power, they have all the same parameters, then again it is
Wernoit, but with different.
Exactly. That's why you saw all those weird pictures, right?
Yeah. With different transmission power and different exponent, changing exponent over the distance. it won't be Bernoulli tessellation,
Right,
and this assumption
Exactly.
will break down. Yeah, thank you.
Which assumption will break again?
Assumption is in which it's assumed that each user is being served by only one base station.
Okay.
Yeah.
So in that case, it doesn't really matter in this case because you are defining your typical mobile to be at the origin. You don't really care about the other mobiles. The reason being that the base stations anyways have to transmit at a fixed power P. That's an assumption. So
Okay.
because of the notion of a typical point, it doesn't really matter in this particular case. It will matter in the uplink. We will see that. And then we are assuming interference limited scenario where we ignore thermal noise. It's again, in these kind of networks, you can safely ignore noise. It is always interference limited. So this is our downlink model. The only thing to remember here is how we define SIR. We are camping to the strongest base station, and all the other base stations are just interference. And since we will be spending a lot of time on coverage, it's important to define what coverage actually means here in this sense. So my coverage probability is going to be a function of the three main parameters I defined. Just to recall, we have lambda i's, which are the densities of different tiers of base stations. You have beta i's, which are target SIRs. And then you have pi's, which are transmit powers for different tiers. Now, if at least one of the base station provides you with enough SIR so that you satisfy the target SIR, so you are in coverage. That's what this basically means. So in other words, mobile needs strong enough signal from at least one of the base stations. And if you just noticed, it is not just coverage. It also completely characterizes the CCDF of max SIR when you assume all these target SIRs to be the same. This is just a CCDF. So this is quite fundamental in this sense. So we have the first main result, which is the coverage probability in this kind of a network. So quite surprisingly, it is in closed form. It is a really simple expression for all those three parameters. And now there is a nice structure involved in this expression. You have, in the numerator, you have a linear function of the densities. And even in the denominator, you have linear function of density. So a little aside here is that if you suppose use in some, say, optimization problem, a lot of people were discussing about optimization problems, and say you have a constraint that your coverage has to be greater than certain value, say maybe C. So in that case, the constraint which you finally get is basically a linear constraint in these densities. So it kind of lends a lot of tractability to the problems. And we have an assumption that your target SNRs or targets SIRs are greater than 0 dB. So what it does is, of course, it won't include some of the cell edge users, because LTE, I think, defines its coding modulation schemes until -6 dB. But still, the fraction of those users is less, and we will see that the results which we get using this analysis, they are actually applicable to that range as well. And we have, just for record, we have relaxed this assumption. We do have result for general beta as well. We have that in Alerton, but it's not really worth including in a talk. It's quite complicated. So now what is the implication? Why did we actually have had this assumption? So what it does is, if you assume that the target is greater than 0 dB for each tier, that means that each mobile has at most one base station with which it can successfully communicate. It cannot connect to multiple base stations. So an easy way of understanding this is that you have two base stations transmitting at power P1 and P2. And the SIR, so SIR at a mobile, if it connects to, say, base station 1, is P1 over P2. And if it connects to base station 2, it's P2 over P1. Only one of these two numbers can be greater than 1. They can be equal to 1 if P1 and P2 are same, but only one of these can be greater than 1. And this actually propagates to countable number of base stations. So, and we have a proof in our paper for this.
Sorry, can I ask a question? I'm trying to understand this first corollary, scale invariance in single-tier networks and k-tier networks. Means you mean by adding femtocells on top of macro, coverage probability is not going to change?
Yes, that's what I mean. At least in this model, that's why I had a discussion with you. So what's happening is that you are increasing the coverage at certain areas, but you are putting some coverage holes in certain other areas. At least putting it in a random way, that's what you are doing. We are not saying that this will happen in a planned way, or at least these two papers are having some planned deployment, but still they see that this is what is going on.
It means the CDF won't change at all.
No. So the way to understand, at least in a single tier network, is that suppose you have a deployment,
yeah,
right? And you say you have a sparse deployment. Now you densify the deployment.
It won't change. Yeah.
Yes. So base station is coming closer, the interfaces are coming closer with the same factor. Why would your SIR change? So that's why the SIR distribution is kind of considered.
But means in single tier it doesn't change because you assume that you have same transmission powers.
Right.
Yeah.
That's why I said it is very interesting in K-tier.
Yeah.
In K-tier you could think, but in K-tier it's not really intuitive. And we will see it's just the case in which your SIR thresholds are same for all the tiers.
Okay.
That's where it doesn't change.
Okay.
It will change in certain other tiers.
Okay. I have a stupid question about the previous slide. Can you please go back? Means, in the first slide of proof, where you start formulating the probability. Here. In the first step, on the left-hand side, we have probability, yeah?
Right.
On the right-hand side, we have expectation. So, without going to the details in the rest of the proof, out of this particular expression, on the right-hand side, we are supposed to get a number.
Right.
And
So expectation of an indicator random variable. Now, you have an indicator random variable. It can either take a value 1 or it can take a value 0. It takes value 1 with certain probability. It takes value 0 with certain 1 minus probability of taking value 1. You just expand it and you will get a probability again.
Okay. Yeah, that's fine. But it should be conditional on something. Means at least means this coverage probability should be linked to some radius or distance.
No, in this case we are actually connecting to the max SINR base station, so we don't even talk about distances. That's why we are getting those form expressions there. If you connect to the closest guy, then you will have all those exclusions and defining interference beyond the closest.
Okay, thank you. But now the assumption has been changed from closest to strongest.
Well, no, we were assuming it to be the strongest right throughout.
No, but previously we were assuming it to be closest.
No, it was the strongest. Max SIR communication model, it has to be the strongest.
In the previous expression.
Yes.
Okay. Okay. For obtaining this result, it will matter means lower, medium, how they are defined.
So I am defining my coverage probability here for P1, P2, P3 equal to 0.9. I'm considering three-tier network.
Okay.
So you have
This is the threshold for which we are plotting these coverage probabilities. Yeah.
not threshold exactly, but these are the transmission probabilities. So your macro.
Okay, 90% occupied, you mean? Okay.
Yeah, run out of battery. Yeah, but could you use that microphone whilst we change the... Sure. Yeah? So sorry for that. No, you just use it like this.
Ah, okay.
We change batteries. Hello? Mr. Discussion here. Now we're good. Hello?
Hello.
Yeah, it's all yours. Okay.
Apologies to the online people. We didn't know that this mic has been turned off. So continuing with this discussion, just keep these three parameters in mind. So you have R, which is representing the distance of a mobile to its closest base station, the one we are going to analyze. And then these interferers, their distances, distances to their serving mobiles, or the mobiles which are camping to them, we represent them as RZ, which is being shown as R1 and R2 here. So these are the only things you need to keep in mind. Now since we are doing power control, the transmit power of a mobile is going to be, the power is going to be a function of the distance to its closest base station, and hence it's going to be something like R to the power alpha epsilon. So we are doing fractional power control, so we keep epsilon to be a parameter which will take values from 0 to 1. So if you suppose keep epsilon equals to 0 here, you are basically not doing any power control. Your transmit power is constant. You keep your epsilon equals to 1, you are doing full power control. That is, you are inverting the complete path loss. And that's what can be shown, easily seen in this SINR expression. In the numerator, you have this term, which is R alpha epsilon minus 1. Alpha equals to 1 means, a complete power control, and alpha 0 means no power control. So that's pretty much what you need to, keep in mind. Now, there is another important thing which we touched a little bit earlier. These R1 and R2 are correlated. The reason being that you have a Voronoi tessellation for these mobiles, and you are putting these two base stations uniformly in their respective Voronoi cells. So you are conditioning on a process. I know it's not that easy to understand during the talk, but just think about it. You have a tessellation, and you're putting one base station to base stations uniformly in each Voronoi cell. Just to understand this correlation, consider two neighboring cells. Now, given the information that I have one base station in a particular cell, that implies that the second base station cannot lie in the first cell. So there is certain dependence, there is certain correlation from this even a toy example. And now the distribution of R, it can be easily found from the null probability of a Poisson process. Now what R was, just to recall, it's the distance of a mobile to its nearest base station. So it can be easily found from the null probability of a Poisson process. So what we know is that since this R is the distance to the closest base station, we know that there is no other base station closer than that base station. So no mobile in the circle of area pi R square. So we have this probability density function for R, and now for the distribution of the distances for the interferers, the RZs, or R1 or R2 in that previous figure. If we assume independence, if you forget about the correlation, if you assume that RZs are independent, we again get a same expression. And we will now show that this dependence in RZs was actually really weak. You could have ignored that and did some nice analysis, and that's what we are going to do. In this plot, we have this CCDF for RZ, and there is this the blue plot is for the actual distribution of RZ, numerically computed for the correlated process, and then you have this actual or analytical expression for the approximation, which is the red one, and we see that these plots are actually quite close. I wanted to explain the other plots as well, but I think I would be short of time. So it's just these two plots. And we see that at least the marginal distribution of RZ, they are quite close and kind of not really affected by the independence assumption. And then for dependence, we cannot say anything from a marginal distribution. So what we do is we study the joint distribution of RZ1 and RZ2. that is the distances of two mobiles to their nearest base stations in their respective cells. And we know that this dependence is going to be the strongest among the neighboring cells. Now, if you take two random variables, corresponding to the cells which are, say, 100 miles apart, that correlation is probably going to die down. So to do a worst case kind of scenario, we consider two neighboring cells, and these RZ1 and RZ2 correspond to those cells, and we plot first, the actual distribution you get at the, the left-hand side. This is the joint distribution for RZ1 and RZ2, the PDFs. And in the right-hand side, we have this distribution under the independence assumption. And we see that they are actually quite close. The only difference is a little, dispersion of this PDF. The reason being that you are removing that constraint which we had before. So in this case, RZ1 and RZ2 are independent. But let's see how this, how this fares in terms of. So I'm skipping this analytical result in the interest of time. Let's see how this fares in coverage probability study. So we have this actual PPP, the true model in which we don't have any assumption. The coverage probability is given by this red plot, and then we have this black plot which is under the assumption, and we see that actually they're really close. So the assumption is not hitting much. I understand it is not analytically really beautiful, but still this model works and give you nice insights such as these. So you have a coverage probability plot for different for various values of this power control factor epsilon. Again, to remind epsilon, so you have epsilon equals to 0, in which you have no power control, and epsilon equals to 1, in which you have full power control. So first observation is that your epsilon equals to 0, which was basically no power control, that is optimal at high SINR threshold. And that actually makes sense. So what high SINR threshold means? So what it means is that you are basically ignoring the cell edge users. You are just considering the users which are lying very close to the base station. And why would they actually do power control? So it makes sense for this expression. And here something really interesting is going on. We will see in the next slide. So here we find the optimal epsilon, which maximizes the coverage. And as we see, the epsilon equals to 0, or the power control factor equals to 0, was optimal at high SINR. But here the values of 0.25 to around 0.3 are optimal for various values of alpha. So here we see that the full power control is never optimal, as one would expect. So so we see that even a simple model like the one we have for uplink, that is giving some nice insights.
But full power control means full compensation of alpha. Channel gain becomes 1.
Yes.
Channel inversion.
Channel inversion, yes.
It's not optimal.
That is not optimal. Otherwise, you would have saved power by that, right? So you are reducing your power by doing power control. All right, so moving on. So can you guys hear? Okay. So moving on, so far we have discussed a downlink and a really comprehensive model for downlink, a simple model for uplink which works and which gives nice insights. And now we will be, looking at the assumptions which we talked about before, and taking, a more fundamental spatial statistics view. And how good is a Poisson assumption? As I said, as I promised at the beginning, we will go over these. How good is Poisson assumption, by the way? For femtocells, we know that the deployments are fairly random, but distribution is still unknown. We don't have data to, support our Poisson assumption, but still it looks okay because, there is some randomness. And in the macrocells, they do have some structure, but definitely not grid-like. That's what we have seen from the data we have so far. For the pico cells, there is some randomness due to the deployment at hotspots. So it is a good starting point, but I think we need to do some more, work and come up with more realistic models. And how good is independence assumption, by the way? So far we have assumed that all the classes of base stations are deployed independent to each other. Again, it works really well in femtocells because if suppose I am a user I don't have information about where the access point is. I will put a femtocell at my home. So the deployment of femtocells is going to be independent of the other tiers. And in picocells and macrocells, again, it is questionable because both are being operator deployed. So there is certain relation in those processes. So can we, so this shows that we do need some in-depth study. And there are tools in spatial statistics. I'll just touch some tools, some really nice tools, but we just need data, and the tools are there, mathematical tools are there. So first, let's check for Poisson assumption in macrocells. We had a data set, the one which I showed in my, I think, second or third slide. So let's check it if that comply to Poisson assumption or not. So we will be doing classical hypothesis testing. So you define your null hypothesis as the following, that your data set is a realization of a Poisson point process. And you define your alternate hypothesis in which you say that your data set is a realization of some other point process which is not Poisson. And due to the finite window size and the random variability, you will never obtain perfect agreement with the Poisson point process, even if data is actually random. Think about it like this. You have a finite window. So there is certain probability of even getting a realization from a Poisson point process which actually looks quite regular. It is not always going to be quite random. So to study this, we construct some simultaneous critical band, or some confidence levels over these summary statistics, and see if the data kind of lies in those confidence levels or not. So the summary statistics we are using here are empty space distance, which is basically, suppose you are standing randomly in space and you are looking at the distance to the closest point. That's what empty space distance is. Now the pairwise distance, suppose you are standing at a point in the process and looking at the distance to the closest points, and then you have nearest neighbor and signal to interference ratio. So as I said, in this case, you have empty space distance. First, we start with the empty space distance. This blue plot is for whatever function we are considering. In this case, it is the CDF of empty space distance. So this blue plot corresponds to the Poisson assumption, and this gray region is basically the confidence level. And now, in this case, clearly your null hypothesis is rejected. It clearly shows that the data was not Poisson. All right. So, but this doesn't tell much about what kind of data it was. It just says that it wasn't Poisson. And now we have a pairwise distance for which this function is defined, a K function. It is quite popular in spatial statistics community, but I won't go over it in detail. In this case, interestingly, null hypothesis is actually not rejected. According to this, whatever metric we are choosing, the data might actually be from Poisson. So we need multiple metrics, we need multiple statistics, and even if one fails, to some extent we can say that it wasn't Poisson. And then this is the nearest neighbor distance distribution, and in this case we could actually say that this is going to fail because this shows the distance of two neighboring cells. So in Poisson you can have cells which are very close to each other, but in the real data you couldn't have until this distance. It's not possible to have cells right next to each other. So in this case, null hypothesis is again rejected. So there is a need to model, as early pointed out, there is a need to model interpoint interaction. Can we do that? So now interactions are of two types. There are intra-tier interactions. There are interactions among, say, macrocell. Then there are cross-tier interactions. There are interactions among macrocell, femtocell, picocell. So we need to model all those. So, just to give you a flavor of what kind of tools are there, I just included a simple multi-class Gibbs model which capture pairwise interaction. In this case, we are not capturing complete interaction over the whole process. We are just capturing interaction between 2 points taken at a time. So so if you suppose have X which denote the given point pattern, the density over that X can be easily defined as the product of these two main terms, where your phi's are the first order terms. and you just had these terms, by the way, in a Poisson process. And then you introduce another, this product, which is basically dependent upon 2 points taken at a time. And hence you explicitly model the pairwise interaction. So a simple model, simple pairwise model, I would say, is so just keep this phi and psi in mind. So if you consider phi to be a constant and psi to be this really simple function, what it does is that you take 2 points. If the distance between those 2 points is greater than some r, you say that, okay, this function is equal to 1. And if this is less than equal to r, you say that it is equal to, say, gamma. Now, if suppose you take gamma equals to 0, what you are saying is that 2 points cannot come closer than r. If you take gamma equals to 1, you are going towards Poisson process. So this is a very nice parameterization, and we call it Strauss process. This is a kind of a first order, I would say, a model, but it still works really well, as we see in this data set. So this is the data set which proved out not to be Poisson. And this is a realization of a Strauss process with parameters being fitted to this process. We see at least the eyeball rolling, we see that the process works really good. Now to give a definitive proof, this is the geometry curve or the SIR distribution we have been seeing for so long now. This blue plot is again for hexagonal model. This green is for Poisson. Again, the same trend. And now we have 2 plots here, basically 2 curves here. One is a black curve and one is a red curve. One corresponding to the actual city and one to the model. And we see that even for this model, we have actually a very simple model. We are able to at least model SIR really correctly. These are overlapping now. This model actually works. I've tested it on various data sets. It works. The reason is that the base station deployments are quite benign. You won't have interaction between, say, a base station which are located again as I say 100 miles apart. It's just the neighboring base stations which matter, and that can be captured by even the pairwise interaction model, and that's what is shown in this plot. So I conclude this talk. We discussed a baseline downlink model, got some nice insights. And even though I call, humbly it as baseline, but still, if you really think, it is quite comprehensive. It has, a good model, good channel model, good spatial model. And then we have, so what it lacked was a sense of load. So we introduced base station activity factor, and we studied how, it can be tied out in the stochastic geometry framework. And then we studied the differences between uplink and downlink. And for a single tier, we proposed a very simple model which gives some nice insights as to how to do power control or what are the optimal parameters. And then we studied spatial statistics for HetNets. It is kind of the work, which I'm starting, because this work I did in my first year of PhD. And now I'm kind of starting towards this area. And we introduced some of the basic ideas which are relevant to, to HetNets. But in this case, we actually need collaborative efforts to collect more data, because without data, you can't do anything in spatial statistics. You need data for HetNets, you need data for femtocells to be able to come up with more realistic models, and maybe in future, even push them towards simulations in standards and stuff. So with this, I conclude, and I would be really happy to answer any questions that you might have.
Thank you, Harpreet. Let's continue with the questions.
Thank you very much for the talk. Very nice work, actually. With this repulsion you introduced with that was kind of manually introduced. Did it change the analysis? And still you assume that it's a Poisson process?
No. Actually, I didn't do any analysis for that. That was just numerical. So
okay.
In spatial statistics, I'm not, constraining myself with analysis. The goal is to come up with as realistic model as I can, forgetting about the analysis.
Okay.
At least we should have some model which works good in simulations.
Okay, means just to have a statistical model based on simulations. Okay, and you compared your work with grid-based model, which was hexagonal. Did you do comparison with the Wiener model or say square-based grid model?
No, I did for square-based. It's nearly the same.
as hexagonal, or
it will again be a upper bound because there is certain minimum distance between the base stations. So your interference is quite benign in that sense. But in vinyl model, I didn't consider because it doesn't really fit in my framework. The gains are kind of constant.
Yeah, but the coverage probability it gives is almost, still it is comparable with the real data, despite of its simplicity of expression.
For the vinyl model?
Vinyl means it's still used in, you can use it for analysis purpose, because for this particular work, some of the expressions require numerical evaluations.
In which work? In this?
In this work, yeah.
Okay, in the first part of the work, there weren't any expressions which required numerical evaluation.
If you assume,
in the uplink, it does.
If you assume like beta is equal to 4, then of course you don't need numerical evaluation. But if you don't assume a general beta, or if you assume fading, which is for example exponential, then I saw.
So basically, let's summarize. In downlink, we did so we had that mega expression which doesn't require any numerical evaluation. Let's go over that expression. Yeah, this is the expression. It doesn't require the assumptions here are Poisson and Rayleigh fading. Now, if you go over to a load-based model, you have an infinite summation. Again, it is closed form, kind of quasi-closed form in that sense, but still you need to evaluate the infinite summation.
Okay.
And then if you go to the uplink, you have integrals. You need to solve numerically. That's the most you would need to do, at least in the theoretical work I've done. And when you go towards spatial statistics, of course, it's more of a numerical kind of a study, because there is so much you can do with analysis.
Yeah, in this presentation, you didn't show the expression. You have one of the Jeffrey's paper which says your coverage probability becomes independent of even base station density. It only remains dependent on the path length exponent beta.
So this is what the slide was, right?
Okay. Your
coverage probability is independent of the transmit power, the densities. It is just dependent upon the target SIRs.
Yes, just dependent on this target SIR. How do you justify this?
So that's why I gave you that example, right? So you consider a macrocell. So first of all, understanding powers is really simple because you consider SIR, you scale the powers, they cancel. But as far as the densities are concerned, so suppose you densify the network, your intended base station or the base station to which you are camping, it is coming closer. And so is the interference. And it turns out that the effect they have is maybe increased or decreased by the same factor, which cancels out.
Yeah, that comes from similar to Rappaport's SINR model, where only dependent on in the angle and the threshold. But the thing is, we are taking out the powers, assuming that they're constant in the very beginning.
No, not for the K-tier model.
Maybe you can continue the discussion offline, and
maybe
we can take another questions. Thank you.
Let's take it offline.
Thank you. I think you just answered my question before because the curves you showed on slide 46 with the Strauss process.
Okay.
I just wanted to ask if this was obtained numerically or by analysis.
It's numerically.
Yeah.
It's
okay.
Numerically. Yes.
Any other question? Yes.
Thank you very much again for this nice explanation of a slightly difficult topic, I guess. I have one question to the beginning. You assume this interference-limited networks, but I'm not quite sure I understand what you mean by that. For example, if I take one random snapshot at a given density, okay, I have some users here and there at the cell edge which are interference-limited. But if this user then moves closer to the base station, gets more power, its rate increases. So I don't really understand what this means.
Yeah, I totally agree with your observation. So what's happening here is that this coverage probability, wherever we are giving it over the whole network. So it's, you can say, kind of spatially averaged kind of coverage probability, right? It's for all the users. We are not separating users based on where they are located, whether they are located at the cell edge or at the cell interior. So what we did was we considered noise, we plotted coverage probability, then we ignored noise, we computed coverage probability. They came out to be nearly the same. Again, the reason is that if you have dense networks and you have all these different types of base stations transmitting, you would have maybe one dominant interferer probably. So hence that noise term will basically diminish, or you can compare you can neglect that as compared to the interference levels.
So you basically assume always it's always a completely new random set. It's not like I can choose to move one base station closer to anywhere.
No, it's a random set.
The interferers are again random.
Exactly. Right. So that's why you have this all these averaging over the spatial process. So that basically means that you are kind of instantiating your processes again.
But how is this then interference limited? I still don't really get it.
So what the argument you are giving is that in macrocells, suppose there is a user which is.
I could improve by raising the signal power. I could improve the rate.
Yes, but in this case, first assumption is that your transmission powers are constant. You can't tamper with them. And secondly, you have different types of base stations, right? So the notion, the very notion of cell edge is kind of bleaked in this. It's not really clear, because you might have a femtocell, even if you are in the cell interior, you might have a femtocell which is very close to you. That might be interfering. All right. So in the high density networks, the idea is that you will probably have one base station very close to you. But we have results for, this was just for the presentation, the paper which I gave. We have results for the general networks in which we don't ignore thermal noise. The only thing is that the expressions are quite nasty, so I just ignore. It's really difficult to explain those or to give some insights on those.
Okay, thank you.
Okay, we will take the last question.
Yeah, thanks for the presentation. It's very nice work, very much inspiring. I think it's important that what you've done, because it helps to understand how to deploy a network in terms of the outage probability of the users. But when operators want to deploy a network, they don't just look at the outage, but also at the average spectral efficiency. Mm-hmm. So in this respect, this is why you need more dense deployment. So have you done any study in that sense?
Yeah, so it's not like, again, giving any guidelines to the operators, strictly speaking, but we have done some studies for the average rate, which can be achieved from this kind of analysis. Again, you can get nice expressions for average rate as well, but we don't have too much insights on how to deploy the networks, because again, in the first step we lose that flexibility. We assume them to be random, at least for this analysis.
Yeah. Okay, thank you.
Sure.
Okay, so I think with this we conclude. Thank you very much. And thank you very much to all of you for being here with us in our second day. And we look forward to see you tomorrow for our Interference and Driver Resource Management Day. Okay. Thank you.
Thank you.